In this video, I will show you how to simulate the impedance of a trace over its distance using the free tools KiCad and openEMS. Even for this completely straight trace, the full 3D simulation shows quite a bumpy impedance response due to the signal reflections from the PCB edges. And because I know that many engineers rely on generic 2D impedance calculators, let's take a moment to explore if and when they can be reliably used. 2D impedance calculators are most reliable if your trace is infinitely long, completely isolated from the outer world, and perfectly straight. All three assumptions are actually never the case in the real world. If you take some time to look at these examples, you will surely notice several factors that can influence the trace impedance. Let's now simply start with the simulation process. In this specific video, I will show you how to simulate the trace impedance via the TDR method, or time domain reflectometry. This method will output the impedance of your trace over its distance. If you subscribe, you will be notified when I upload a video on how to simulate the trace impedance using scattering parameters. They would output results similar to those from a vector network analyzer, or VNA. Combining both methods can give you very useful insights. The first step is to open FreeCAD. Inside FreeCAD, create a new project, run the FreeCAD to openEMS macro. If you're new to this channel, please first watch the tutorial video on how to install openEMS properly. The link to the installation tutorial video is in the description. To enable the KiCad import button here, just close and restart the macro, because the button is not enabled the first time you run the macro. Mark this checkmark, and now let's import the KiCad layout. Mark the two objects, change to the part workbench, and create a simple copy of them. Delete the two initial objects so that only the simple copies remain. Rename the PCB object to FR4 and the copper object to PEC. PEC stands for Perfectly Electric Conductor. I'm just using PEC instead of the term copper to have an easier time later to assign the correct material properties for the copper. Now create a box and call it air. The air box should extend at least 3 mm above the trace. In all other directions, make the air box at least 1 mm bigger than the PCB. If the boundary is too close to the signal, it would result in a wrong impedance simulation result. Now mark all bodies and change the transparency to 90% so that we can see what is going on inside of the objects. Make a copy of the air box and call it H field. Make it 10 micrometers thick and place it in between the top and the bottom layer of the PCB. Now copy the airbox again and let's create the input port of the simulation and place it at the starting point of the trace. Attention! The port works most reliably if it intersects with the trace in the ground as shown here. We have now created all the components, restart the FreeCAD to openEMS macro, and let's work through the tabs. I will for now skip the object assignment and come back here as last step. Let's define the grid in the Grid tab. Define the materials in the Materials tab. In the Excitation tab, we will add a step function. Let's now change to the Port Settings tab and add an input port. Since openEMS injects an electric field rather than a voltage, here is how to convert the field value into a voltage value. We will skip the Lumped Part tab and add a magnetic field probe or H-field probe in the Probes tab. In the Simulation Settings tab, we will set all the boundaries to PML. PML stands for Perfectly Matched Layer, and it tries to mimic an extension into infinity. Let's now go back to the Objects Assignment tab and assign all the objects. Once done, save the settings file and generate a Python script. Let's now go to the folder that has just been created and edit the Python script. As the code generator does fail to generate the step function, we will just edit ourselves. The second change that we will make is to make the H-field probe perfectly flat. The simulation will also work without changing the thickness of the H-field probe, but reducing the thickness will reduce the file size of the generated field dumps. Now let's run the Python script by double-clicking on it. After the first few thousand time steps are simulated, you can open the voltage and current dumps, and you will get the impedance at any time step by simply dividing voltage over current. For this, I will copy the data over to LibreOffice. Of course, you can also use Microsoft Office as well. And then let's divide the voltage column with the current column. Let's add a line graph. Once the signal reaches the end of the trace, the impedance will get very high, so we know that this is the end of the trace. I will now reduce the display range for the impedance between 0 and 100 ohms. After overlaying the impedance with the trace, you see that the impedance, even with the straight trace, is not constant. I repeated the simulation with a longer trace to see if something changes. This trace is now 30 mm long, and we still have a very bumpy impedance, even though the trace is completely straight and seemingly far away from the PCB edges. So where does this bump come from? This bump is the reflection that we get because the signal was reflected at the edge of the PCB walls. If you investigate further, you will find out that the second bump comes from these corners, and so on. The conclusion is that the trace is very sensitive to its surroundings. The solution to this effect is, as most of the times, shielding. So let's try shielding the trace with some vias. This setup here is called a grounded coplanar waveguide. The previous setup was a simple coplanar waveguide. We now get a very flat response, but sadly the injection point has a dip. I will show you in a bit how to remove this dip, but first let's also introduce a layer change. Making a trace thinner can reduce the trace impedance/resistance in DC and also at higher frequencies. Here now is the result after I adjusted the trace widths. There are also ways to tackle the remaining wobbles. This might be a topic for another video. As a side project, you might also want to check out this GitHub page. It features a simulation of the signal transition from an SMA connector to a PCB. And it shows some useful tricks on how to match the impedance. Thank you for watching and see you in the next video. Oh, I almost forgot. The more stable impedance of the grounded coplanar waveguide comes from the fact that it has much lower emissions compared to a microstrip and even compared to the simple coplanar waveguide.